Hello, my name is Hartmut. I'm working at Louisiana State University as a professor at the CS department and a senior scientist at the Center for Computation and Technology. And what we do in the Stellar group, by the way, Stellar is not because we are Stellar, well, we are, but it stands for Systems, Technologies, Emergent Parallelism and Algorithm Research. Really fancy name, you like it. And I would like to present a couple of results of our work we've been doing for a couple of years now in the area of how to manage parallelism, how to manage asynchrony in C++. And I admit I'm a bit sneaky here because the original title of the talk was something related to HPX. And the title now is Managing Asynchrony in C++. That doesn't mean that there won't be any HPX in the talk, because everything what I will present is based on that library. But I wanted to shift the focus a bit to a more generic problem set many people might be concerned with when it comes to parallelizing their work. Okay, let me start with an analysis of what we have today when we look at the computers we have at our hands. And let's have a look at some historical trends in the evolution of the technology which is used in our computers. This graph shows you, it's probably you have seen that graph, shows you the evolution of the density in terms of transistors on the chips, the power requirements, that's the blue one, the lower blue one, and the dark blue one is the clock speeds of the processors we use. And as you can see, around 2003, 2004, these graphs start to kind of level off. And even if Moore's law is still in effect and is still true for the transistor density on the chips, the increasing power requirements and the resulting clock speed limitations, which started to hit in the early 2000s, are still in effect today. Essentially, what we have is a lot of transistors and a lot of silicon, and people don't know what to do with the silicon. And they came up with the idea, hey, let's do 2 cores on one chip. And many cores were born. And if you look at what we have today, this trend just continues with exponential speed. Another historical trend I would like to outline is what you see here is a statistic of the top 500, the 500 most powerful machines in the world, and it shows the percentage of technologies used in those machines over the years. So that's 2013. The big blue one are clusters, multi-node clusters, where you connect commodity nodes essentially with a very fast network. And the other dominating part are the massively parallel systems, which are based on GPUs nowadays, where you have general purpose GPUs in the systems. I'm showing you that just to make clear that clusters are there to stay, and that technology is what we have to expect for the next years. And yes?
You said GPUs make up the smaller part of it in the recent years, but we didn't have the technology at the time where the graph starts around.
Right.
So what was MPP at that point?
So the question was, what was MPP before we actually had GPUs? There were other technologies which are have been developed over the years, like massively parallel single memory image systems, which had many cores sitting around a memory, like the early Crays or other machines. It's just the same technology or the same concept behind it, which is now GPU-like, where you have many cores doing the same thing at the same time, sitting on some, doing massive parallelization. Yes?
If I recall correctly, the distinction that they make in the modern top 500 is whether it's a proprietary interconnect or commodity interconnect between cluster and MPP. usually the MPPs are even still, you know, commodity processors or very similar.
Okay, the comment is that the distinction which is made usually on the top 500 list is based on whether it's a commodity or a proprietary interconnect between the nodes. And I have to concur. My point is really just to show that clusters are here to stay. And that technology is what we will see even in those machines Dan was talking about yesterday, right? The exascale machines, which gives us exaflops performance, or supposed to. And the last thing I want to show is the trend in increasing the rate of cores per socket over the years, and how that is distributed on the top 500 list. And you can see that we now have a large part, or almost all machines have more than one core in a socket. So again, we are facing a technology which drives us towards massively parallel, massively multi-core machines. And if you think about those exascale machines Dan was mentioning yesterday, what we will see is millions of nodes with billions of cores. What that means for us programmers, well, I can't think about two things at the time. My wife can think about two things at a time, perhaps. No, I can think about one thing. She can think about two things at the same time. But on the other hand, we are supposed to write programs which do a billion things at the same time, always and at any point in time. Just imagine how that can be done. And that's a big challenge. And if you look at the machines we have today, which are in the range of a petascale, 20 petascales, petaflops perhaps, if you analyze the efficiency of the applications which are run on those machines, you will see that most applications don't use those machines with efficiencies better than 10 to 20%. That means 80% of the energy we pump into those machines, which is in megawatts, is just boom. And that's caused by the programming models, by the way we program those machines today, because we don't understand how to program those machines efficiently. And that's what I want to kind of try to address, and to give some hope that there are ways to overcome the way we program big machines today. And you might say, hey, I don't care about exaflops. I won't never in my life do any programming for an exaflops machine. But the history just shows that what was on the supercomputers, the cutting edge 10 years ago, is today standard common practice on my laptop. So those technologies we develop for the exascale and for the top-notch machines have direct impact on what we do every day on our cell phone. Well, that's not the most modern machine, not the biggest machine we have. It's a Kraken machine, which has roughly a petaflops. I'll show it here just because it's a pretty picture, just to give you an idea what that means. And that machine has only 9,000 nodes. Only 9,000 desktop PCs just put into a rack. What an exaflop machine will have 1 million of those, just to give you a scale of what we are talking about. Okay, that's technology. The other problem we have, or the other thing we have to remind ourselves, is Amdahl's law. You might have heard about Amdahl's law. I'll give you a short overview. If you parallelize a program, you probably won't be able to parallelize a program 100%. You will probably, in the best case, 80–90% of your program will be parallelized, and you will leave 10% or 5% of your program being serial execution, because you can't parallelize that. I/O, networking, whatever. But what Amdahl's law says, and that's a very simple formula, S stands for scalability, for speed up. P is the proportion of parallel code I have in my application. It's a number between 0 and 1. And N is a number of processors or cores I'm throwing at my problem. And what it says is, if I have only 10% non-parallelized code in my application, my maximum theoretically achievable scaling of my application is 10. So if I leave 10% non-parallelized code, I can't get faster than 10 times the serial code, no matter how many resources I throw at it. So if I throw 65,000 cores at it, it won't run faster than 10 times the serial version. I can't do anything about it. And if you think about it, it's very simple to understand, because if I have some serial pod in it, I can't get faster than that serial pod no matter what I do. So the conclusion is we really have to strive for a 100% parallelization of our codes in order to use 1 billion cores. Okay? And using 1 billion cores, having a scalability of 1 billion means that my serial part in my application is not larger than 10 to the minus 9th. Essentially, I have to parallelize the whole thing in order to use those machines efficiently. What are the reasons why our applications are slow, besides Amdahl's law? I think there are 4 reasons. I might ask you, and you might all come up with other reasons, but I believe all those reasons we have which limit our scalability are derived from what I call the 4 horsemen. First is starvation. Starvation means it's that I have insufficient concurrent work in certain parts of my system, so that part of the system is just starving for work. It can't do anything. Latencies. It's the time distance to remote services like network latencies, memory access latencies, and things like that. Overheads is work which I have to do in my parallel version of my code, which I wouldn't have to do in my serial version of the code, because I have to manage that parallelism, right? If I have 1 million threads, I somehow have to manage those. I have to schedule them, I have to allocate them, and so on. And the last one is waiting for contention resolution. Contention is kind of the opposite of starvation. Is if you have too much work in certain parts of the system, you know all that, right? If the interstate is crowded, even if there's no accident, everybody drives slowly. Too much cars to go through the same funnel. And that's what contention does. And we chose those terms wisely, well, and that helps you remember those 4 horsemen very easily. It's slow. And the problem with those 4 horsemen is that in addition to Amdahl's law, they impose a upper limit onto scalability in terms of strong and weak scaling onto our applications. And that's in addition to what Amdahl's law already theoretically imposes on us. Dave, you have a question?
Did you explain before what weak and strong scaling are?
The question is, what is weak scaling, what is strong scaling? Good question. Strong scaling is the analysis of how much faster do you run if you don't increase the size of your problem, if you just throw more resources at it. Same metric size, but you more cores to it. Weak scaling changes the problem size while adding more resources. So if you have a 10 by 10 matrix run on 1 core, then on 10 cores you run a 100 by 100 matrix or something like that and do an analysis. Weak scaling is usually easier to achieve, because especially if you have embarrassingly parallel problems where you have independence between the parallelization, right, where you don't have these cross-references, then weak scaling, just you scale out and use that. And that's how people usually use those big machines. They just run 1 million of independent processes there. Strong scaling is much, much more difficult to achieve, and I want to focus on strong scaling during this talk, because that's something people usually ignore. And if you read papers, nobody talks about strong scaling because nobody gets it, because of Amdahl's law. Okay, other questions? So our challenge is, we need to find a way to fully parallelize our applications. We need to defer the 4 horsemen, because those essentially are the 4 horsemen. They kill our performance. We need to provide manageable paradigms for handling our parallelism, because we have feeble minds, right? We can only write programs which we understand. And we not only want to write programs we understand, we want to be able to debug them. Well, there's that notion that debugging is 10 times more difficult than writing code, and if you write code as clever as you can, you're by definition not able to debug it. So we have to solve these problems. We want to expose the asynchrony to the programmer without exposing concurrency, which is important, because concurrency means dealing with concurrency. Have you ever written a multi-threaded program and dealt with concurrency and with data races and with all that crap? So we want to hide the concurrency. What we want to expose, the parallelism. And the last thing, and that's already taking kind of running ahead, is we want to make our data dependencies in our algorithms explicit so that we can parallelize them. And I will give you some examples of that. The main notion, and if that's the only thing you take away from this talk today, stop thinking about threads. Threads is a non-entity. Threads are done by the runtime system, by the operating system. They do that. But stop thinking in terms of threads when you write your algorithms. And that's why OpenMP, as nice as it is, you might know OpenMP, right? That's a pragma you put on a loop and the compiler magically parallelizes that loop for you. That's why OpenMP is so bad, because it forces you to think about how to best possibly partition your algorithm into those threads. And it doesn't solve your parallelization problem. It just kind of hides it. Yes?
Are you using parallelism and concurrency synonymously there in that previous slide?
The question is, do I use parallelism and concurrency as synonymous? If that appears to be, then the slide is bad. Parallelism is something fundamentally different from concurrency. Concurrency is all about synchronizing access to the same things in memory, whereas parallelism is all about doing many things at the same time. And I want to focus on parallelism, and I want to hide concurrency from the user because that's a really, really difficult part. Okay, runtime systems. The whole talk and all results we will present are based on HPX. HPX is a runtime system you can compare with your C++ runtime library. You link your application with it, and it gives you additional services. And what HPX does, it just gives you additional services to what the C++ runtime library already provides you with. Since all the examples in that talk are based on HPX, I just want to give a quick overview, but I will hurry up because otherwise I will run out of time. So if you have questions about HPX and I skim over it, just let's talk about that afterwards. HPX is a C++ library which we try to expose a uniform, very C++ C11 standards compliant interface to the application, but still allow to write code which runs seamlessly on a laptop, on a cell phone, and on a supercomputer without having to be redone. You just recompile it on the machine, and it will magically use all the resources you throw at it. It is designed to allow fully asynchronously written code with hundreds of millions of threads. And I really mean hundreds of millions of threads. Does anybody has done pthread programming? Well, a couple of hands, all of you. You probably never have used more than 100 of them. Perhaps 1,000, perhaps 10,000. But I guess you never used a million or hundreds of millions of them. And that's the crux. We need to use so many threads, otherwise we can't use a machine, right? The other takeaway, HPX is boost license. Use it. Contribute. Get back to us. A couple of governing principles, and I will skim over those, and I will get back to those during the talk all the time. And even if you don't completely understand what they mean, it will get clear over the talk. We provide a global address space to the application, so the whole machine is one address space. And the reason is so I can move things around, right, from one node to another node without updating the references to it. Very much like a virtualization on we have today. It's message driven. That means we try to be proactive, sending messages, and when the message is received, something happens. We have very lightweight control objects which are to be there to replace these global barriers. The common paradigm we have in parallel programming today is MPI, Message Passing Interface. You might have heard about it, which imposes a lockstep style of programming where all nodes do the same thing at the same time over the whole machine. I simplify, but that's the crux. And the problem is that if one of the nodes takes 10 times longer than the others, All others will wait for the slow guy before they can continue. That's what global barriers are, and that's one of the main reasons for contention, for starvation, for all of those problems. We try to hide the latencies of the network behind useful work. And an important one is fine-grained parallelism of very, very lightweight threads. And I talk about, when I say lightweight threads, I mean threads which last 10 microseconds, 20, that's it. So threads which really are created to do one single thing and then go away. And the reason for that is, well, if you have a box, you fill it with marbles, and the marbles are large, you have a lot of space in between the marbles. If you fill them with very small, tiny things, you fill up the whole thing very nicely. And that's what happens with parallelism in machines. If you have these humongous threads, you end up with a lot of waiting time in between during synchronization and so on. Yes?
So how are you able to spawn a thread that fast?
The question is, how do we spawn a thread that fast? Well, that's one of our secrets. We use a user-level threading system with our own scheduling. And our lifetime for a single thread is sub-microsecond. Creation, scheduling, running, deletion, 800 nanoseconds. So that gives you a minimal overhead and allows you to do that. But there are limits, and I will come to that. I really have to hurry up. Well, let's skip that. One thing, what we do to make the API manageable, we just looked at C++11 and said, hey, cool abstractions, let's use those, and rewrote them. And we had to rewrite them for several reasons. One is, most compilers don't have an efficient move-enabled implementation of bind, function, tuple, all those types. Well, some compilers have nowadays. Yes?
Just to clarify, by that he means for a long time the version that was in the GCC did not work, period.
Okay, so the comment is compilers have been better at it, and nowadays compilers might have these things implemented. But the other reason was not only because we want to have move-enabled objects, but we want to be able to send those objects over the wire. We want to instantiate a bind, wrap it up, send it over, and invoke it on a different node. And that is not possible with standard things. That guarantees us full type-safe remote operation, so we can invoke something remotely. And everything what you can do with functions, you can do with remote operations in HPX. And all those data types are remotable, bind, function, any, and can be used with actions, and you will see how that works. If you look at C++ and just think about invoking a simple function which gets some parameters and returns a value R, then that's what C++ gives you. Synchronous invocation of a function locally. Right? Very simple. That's what the standard library gives us. Asynchronous invocation of a function, run it on a different thread with async, and doing it lazily. So pre-bind arguments and invoke it later, and combine the two, async and bind. But what we provide with HPX is another extension of it. We added a fire and forget mode, where you just send it off, and you don't care whether it does what it's supposed to do. It never comes back to you. And we extended the notion of synchronous and asynchronous invocation with what we call an action. An action is essentially just a function object which causes an operation to be possibly remotely invoked. So you have a function there, you call that function object here, and magically that function gets invoked over there. The future. A closer look. Let's look, what is the future? Those of you who have attended Rob's talk yesterday, he already talked about standard future and what it does. A very quick overview. A future is an object representing a result which has not been computed yet. So it's a placeholder, it's a proxy. And essentially what happens is, in one place you create a future or you get a future, and at some point you need the result from that operation. The future makes the operation run on another place, and if you need the value at that point and the value has not been computed, that thread gets suspended. Other work can be done on that core, and whenever the value comes back, the original thread gets resumed and doesn't even notice that it got suspended in between. And we will see some examples for that. So it enables very transparent synchronization with producers, hides the notion of threads, makes asynchrony manageable, that's what I claim, and very important, turns concurrency into parallelism. But we will see examples. Well, that's a very simple example. Let's say we want to compute the universal answer to the life, to the universe and everything else, which is, we all know, is 42. And we construct a computer which is called Deep Thought, which says, yeah, come back 7 million years from now, and I will have the answer for you. So I do an async, spawn that universal answer thing on a separate thread. It gives me a future. And 7 million years later, I come back and say, hey, now give it to me. And it will say, yeah, here, 42. That's the answer. So it's a very simple way of building parallel applications and hide it behind the future just by representing the result of, which has not been computed yet at that time, in the future. And whenever I call get on that future, it will either suspend and wait, or if the result's already there, it will give it to you immediately without suspension. So it's a very nice concept, and the whole talk is built on top of that. Is that clear? Good. I was thinking, what algorithm could I use during this talk to present all these concepts? And I thought, let's do something very simple which fits on one slide. And I chose Fibonacci. Everybody knows how to calculate Fibonacci. Those guys, you are grinning, you know, that's a standard example for parallelizing things. And it's very stupid, because what we do, we calculate Fibonacci with complexity O2 to the power of n, which is the worst thing you can do, I admit that, because you can calculate Fibonacci in logarithmic time. But the reason why I chose that example is it represents a whole class of very important applications, namely all applications which are tree-based recursive or game theoretic applications, graph traversal problems, which are everywhere. So even if I talk and if I show everything in terms of Fibonacci, everything is true for any application from that class, okay? So don't shoot me because I'm using Fibonacci and it's stupid. I'm just trying to make a point. Just for you to show that it's really 2 to the power of n, well, that's logarithmic. That's the number of Fibonacci I want to calculate. And Fibonacci 40 will execute that function roughly 5 billion times just by recursing into it over and over and over again, right? So each level invokes Fibonacci on twice with n-1 and with n-2, and each of those recurses into itself 40 times until it gets to 1. It's characterized by very tightly coupled data dependencies, which is always a limitation for parallelization. And what I chose to do in the first attempt is let's spawn a new thread for each of the invocations of Fibonacci. And the code looked like that. Let's look over that. Fibonacci, if we know the answer, we just return 2. And what we do, we launch Fibonacci itself for n-1 on a new thread and execute Fibonacci of n-2 on the same thread directly. Okay, a new thread, and the other one gets executed directly. And in the end, at the return statement, we just join them. We say, okay, I wait for that guy to finish, and once that guy is finished, I can compute the result on that particular level of my tree. Yes? Yeah. That's to make a point. And we will see what that point means. So the question was, I'm using deferred. And you might already guess that this is a real problem, because what deferred means, it gets executed only inside get, which defeats our parallelization. But the first attempt was just that, and I admit I did that in my first attempt, because I thought, hey, I know that I better not create a million of threads at the same time, because that blows my memory requirements. So let's defer it as much as possible. But I ended up with that, which means That's Fibonacci. That's logarithmic execution time. And no matter how many cores I throw at it, it's essentially same performance. No parallelization is going on. And the worst thing is, hey, it's 100 times slower than the serial code. Well, okay. So if you look at the same data from other perspective, it shows the number of cores, the time, and that's the Fibonacci. You see that it doesn't scale at all. I throw more cores at it, and it takes the same time to execute. So no parallelization happens. Worst thing what can happen to a guy who tries to parallelize something, it doesn't scale. Shit. What can we do? Well, one, you already identified it. It's a deferred one. And that's easy to fix, and we will fix it. But there's a second problem in that code. Who can see that?
Other than it's recursive?
Huh?
Other than it's recursive?
Well, other than it's stupid, certainly, yes. Right. That one. I'm very careful not to use the word block in any way during that talk. I'm always talking about suspension. And that's very important in HPX, because whenever you hit a get, other work will be done on the same core, which is available. So nothing blocks, really. It gets just suspended and delayed. So let's fix that one, and that one is more complex to fix, but we will see how that works. Okay, async, a bit better. You see some diversity when you add cores. So that means when you have 24 cores, you're much faster, 10 times faster than with 2 cores, which is good. Still 100 times slower than serial code. So it didn't solve our problem, even if you had the right idea. By the way, that line is if I use std future and std async instead of HPX future and HPX async, just to give you a relation. So it's even in that area where it's kind of aligned, it's still worse than what HPX can give you. And that's the scaling curves of the different cores. So with FIB28, it starts to scale even. You know, when you add more cores, it starts running faster, right? You have a speed up of almost 7 for Fibonacci 20. We are getting there. So what's wrong? While the scales, it's still 100 times slower. The problem is that each future creates a new, or for each invocation of Fibonacci, we create a new future, which spawns an HPX thread. Okay, what's an HPX thread? Even if the overhead is sub-microsecond, each thread is assumed to be suspendable. That means we have a separate stack segment for each thread. Well, the invocation for FIB28 roughly is, I don't know, 5 million times. So that means we have 5 million stacks laying in the system. It thrashes our virtual memory. It uses up physical memory. It just destroys our TLB. It thrashes TLB and other nice problems. And that's the reason why it's so inefficient. And each thread has minimal work in it. Even if it's sub-microsecond, the work we execute is in range of 15 nanoseconds. So we create a thread which needs a microsecond, but we do work for 15 nanoseconds only. So it can't scale, right? What I suggest is let's introduce a notion of granularity for parallelism. When I talk about grain size or granularity, what I mean is increase the work which we do in one thread. And the way I propose to do that in our Fibonacci is just to say, hey, we introduce a cutoff at which point we switch to serial execution below. That increases our amount of work we do in each thread, and we can control that, how deep that serial part is, and we can do an analysis. And that's easily done. Let's say we have some threshold, and if you're below that threshold, we just do the serial execution, which consumes a considerable amount of time, way above 50 nanoseconds. Okay, what do we get? This time I'm using Fibonacci 40, and that's the time the serial execution takes. Who would venture how that curve looks for our parallelized algorithm when we increase the serial threshold? So that's the threshold. The larger the number, the larger the amount of work we do in one go, and that's the time. Any ideas? Well, it looks like that. That means that if we start controlling grain size, we have a very powerful leverage to actually achieve effect in parallelizing it. We run 10 times faster than the serial code in the best case. Right? So I increase my grain size, it gets larger and larger, and at some point I hit a sweet spot. And that's a very interesting observation because, well, if you think about it, in that way, edge, we just have too many threads and too much overheads in the system, so we can't run fast. And in that thing, our threads gets too large, the marbles get too large, and the synchronization time takes over. And at some point it will hit the serial execution again. If we do everything in serial, we get the same execution time for both. Yeah, overheads. Well, that's all I said about. Okay, let's try do more. And what we did is we looked at what the proposals for the standard which are currently in there. And one of the proposals for the new standard is some improvements to standard future and related APIs. It's document 3634, the link is here, you can read about it. Essentially what they introduce is a couple of extensions to standard future, which allow to wait for more one all. You pass several futures to it and it will wait for all of them. It gives you back a future which represents the overall result. Very nice. When any returns when the first one is ready. Another extension is they add a member function to future.then, where you can give it a function which gets executed whenever the future gets ready. Okay, so kind of continuation style. You say, hey, do that for me whenever you get ready. I'm not going to wait for you, but do that for me whenever you are in your own time. Unwrapping futures is a nice feature we will see we can use. Some async might return a future of a future to a t. But future has a member function unwrap, which throws away the outer future. You don't need that, right? The outer future would wait for the inner one anyway. So you only have to deal with the inner one. And that's very useful. And the last one is they add a make ready future global function, which creates a future from a value, which is ready at construction time. It just encapsulates a value for you in the same way as a future would give you some remote operation. And you will see what we can do with that. Yes?
So what's the use of having nested futures?
We will see an example in a minute. So the question was, what's the use of nested futures? I will show you an example, okay? I just have to brush through that, otherwise we will run out of time. I want to introduce you to a technique which we developed at our group, which I call futurization. And it's a very interesting but very simple transformation you can apply to all your parallel or to all algorithms which you want to parallelize. It delays direct execution in order to avoid synchronization. So this is about getting rid of that get of the last synchronization point. It kind of turns straight code into futurized code. Whatever that means, we will see that. So the result is that the code or your algorithm no longer calculates the result immediately, but the code will instead generate an execution tree which is structurally conforming to your initial algorithm and which is represented by futures depending on futures. So your algorithm not longer calculates the result, but constructs that tree. And when that tree gets ready, it unravels at its own speed without having to wait. Because whenever two children are ready, or more children, the next node gets triggered, and it will propagate the value up to the root of the tree. And I hope I can make that clear with some examples. The trick is that the tree when you execute the tree, you get the same result as when executing the original algorithm. And the tree can be executed fully parallel with full speed without having any synchronization points in there. We will see how that works. There are three very simple transformation rules you can apply to any algorithm, any That's the trick. As long as the right-hand side has no side effects, and I will point that out, which is very interesting. Essentially, if you have a function which normally returns t, you convert that into a function which returns a future to a t. If you have an r value, which is n, you turn that into a make-ready future of n. And if you have a function invocation, so some value on the left-hand side and something to do on the right-hand side, which could be not only a function but some expression you calculate, you turn that into a future n equals to async and wrapping that expression you have on the right-hand side. So that's futurization. And if you apply that to our code, let's see what we get. So that's a Fibonacci a bit reformatted so that the new code will fit in there. Well, that's the first thing, right? We want to turn our function into something which returns a future to whatever we will return. The next two lines are easy because that's R values. We just wrap them into ready futures because we have the result. So why do some asynchronous thing? We just wrap them up into pre-initialized futures. That one is more tricky. And here you get that future in the future. Because that thing now returns a future, async will return a future to that future, right? Well, that one is obvious. We just turn that into the future because that one returns a future now. So we just assign that. And the tricky part is that. What do we do with that plus in between here? We use when all. We say when all, when both of the futures are ready, do something. And that do something is inside then. And that's a bit of a mouthful. So I took that apart for you just to digest piecewise. So when you have when all, these two futures, that is a future to the future. We have to wait on it to unwrap the outer one. And that's the one we got, right? And that when all returns a future which represents the result of the computation of whatever is happening here. And the way the standard or the proposal specifies it, hey, let's return a future vector of those futures and wrap them into a future. Okay, so the overall future returns a vector of those two. And we know that those futures which are in here are ready, because otherwise wouldn't have returned, okay? So we got an f, and now we attach our then to it, and that what the function which is doing is receiving that very future it got attached to. So it's again the future, vector, future, and so on. And we just have to unravel it, right? We do a .get on the outer future, we get that vector, and then we do v0.get plus v1.get, which is the two values of the two subtrees we actually calculated. And that thing is returned from the inner function, and that then has a nice feature that it gives you a future representing the result of the inner function you attach to it, which is just cool. It allows you to chain those things. You can do .then, 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 and each of those get invoked with a future representing the result of the previous step. Well, and we return the result. So let's take a step back from that. What did we do? Does it still calculate Fibonacci? I claim yes. I just have to wait for the future which is returned from it. And what we did, we took the original algorithm, kind of mangled it in some automatic way, so that's something a compiler could do, and created an algorithm which, instead of calculating future, creates a dependency tree of many futures, which, when unraveled, give me the result I'm looking for. Okay? Very powerful technique. And the trick is, and that's what I want to convince Joel for years now, to add that to NT2, just annotate your types, and that thing can be done at compile time by the C++ compiler. That transformation, so we don't have to do it manually. And what that means is that we auto-parallelize our algorithms, and the compiler, which has no clue about parallelization, just does it for us. Isn't that cool? Yeah. The question is it efficient? Well, that's what we had before. Our third attempt was the granularity control with the one async. If we now use the .then solution, the futurized solution, you might be disappointed. But if you look closer, there is hope. There is hope. We are faster, a tick faster than what we could do before. And now imagine, we seem to be much more at runtime. We create that whole tree of hundreds of futures, and we are still a tick faster than in the case when we didn't do that. And the reason is because we essentially got rid of the .get, of the synchronization point, which made us wait on each of the step for the other subtree to finish. And that wait time is amortized and helps us to get faster. Okay, do you get that? Good. Well, there's still a .get. But this .get now waits for the construction of the right subtree and not for the calculation of the value. And luckily enough, we can get rid of it just by doing unwrap on that first thing. Gives us just in the future that future of the future represents. And now we don't have any .get anymore. Ta-ta! Guess what? It's the fastest thing so far. Even if we seem to do more and more and more in our code, we are getting faster and faster and faster. I really like that. So far, we are, and by the way, that's real code that runs with HPX. So, and Boost has some preliminary implementation for when all and for .then and for that stuff. So you can try it out at home without using HPX. Can we do better? Yes.
Yeah, with some in some point you introduce a vector, and I'm not sure why it was introduced.
That vector.
Right, but
That one? When all returns a vector containing all futures it's getting initialized from, or it's getting called with, because you don't know how many. You can call, it's a periodic function. So you can get n of them. And that's why the signature is it returns a vector of those guys. Did I repeat his question? Okay, the question was, where does that vector come from? Yes?
If when all is guaranteeing that all of the futures it's passed already, when it satisfies the outside future, why does it return a vector of futures rather than a vector of results?
The question is, why does it return a vector of futures and not a vector of results if we know, because we already know that those values are available, because otherwise it wouldn't have returned. The answer is, a future, the operation might fail, in which case .get throws an exception. So you can be in control whatever happens with the futures you get. It's done that way. It's error handling. Yes?
Why is the vector inside a future?
Because .when returns a future representing the result. The question is, sorry, why does it return a future and not just a vector? Because .when returns a future representing the result of the whole operation in one future and not in hundreds of them.
Sure, but
It's just specified that way. It's very convenient because you can compose things that way. You can use the result of .when, of when all, with other when alls. You can chain them. And I'm almost done, and I know Vinay will just beat me up because I'm a bit over time, but I will really speed up. That's what we talked about. One more proposal in the standard, to the standardization committee. It's called resumable functions, which is a bit tricky, but very useful, and we will see why. We have a large amount of overheads in HPX because of the stack creation. So we want to get rid of that stack. And the reason why we have those stacks is because at the suspension point, we need to keep the state of that operation somewhere in order to be able to return to that point and to continue. But what if we were able to get rid of that stack segment? So we could run everything on one stack segment. Wouldn't that be cool? And that's what resumable functions are about. That's how it looks like. You annotate your function as being async, and that read returns a future. So you would suspend here at that point because you wait for that future. Or when you wait for that future, at that point, you would have to suspend because you want to wait for that read operation. That await statement and that's a new keyword which they want to introduce, tells the compiler to generate tricky code. That tricky code will return from F at the point of the await. Just think about it. It doesn't wait for the final return. It returns immediately from F and gives it a future representing the final result of the function, which will be computed at some point. Yes?
With that thing, there's a way you can do this with library only, with boost coroutine, with almost the exact same syntax.
You can't. You can't. The question was, you can do that with boost coroutines with exactly the same syntax.
You can't, is a statement.
HPX is built on top of coroutines, so I exactly know what you're talking about. And all those things I was showing before were an attempt to find a library-based solution to that. Well, I will show you how you can do it with a library solution and with coroutines, yes. But it requires some trickery, and I will get to that, okay? So wait for a minute, please. So it returns, well, you can't return at that point from F with a library-based solution. You need compiler support for that. The compiler needs to kind of rewrite that function, put all local variables onto a separate heap segment, so you can leave the function without leaving anything behind on the stack. Requires compiler support. Local variables and parameters have to be placed in heap allocated memory. The code has to be transformed. Just imagine you're passing a pointer to a local variable of a function into a called function and things like that. So the compiler has to take care of that. And has kind of surprising semantics because it returns at that point. So any side effects code after that await might have not been executed when you return from that function, which might be surprising. And the other thing is, even if you return an integer here, it actually returns a future of an integer. So there's a mismatch between the return type you see and the return type you have. So it's controversial. Let me put it that way. But its advantage is you can do it on one stack segment because the stack is left in a virgin state when you leave it. Simplifies code, and you get more asynchrony. If you apply that to our future function, we just do async. Await. Ta-da! That's it. Yes?
The stack that's allocated for this resumable function, how is the size measured? Because it could call another function after the await.
The question is, how is the size of the stack segment measured if I create that? Each function gets its own heap allocation, so a compiler knows what happens inside that function. And each recursion creates a new stack segment for that new function. That's why it's possible.
I can call a normal function after the await, and then it's difficult for the compiler to argue.
Well, you're acting on the... no, sorry, let me repeat that. What happens is the compiler doesn't allocate a stack segment. The compiler allocates the local variables and the parameters on a heap allocated piece of memory. But the stack stays the normal stack you're dealing with. So it has a normal size, and you do everything on that stack. It's just when you return from when you hit an await, you leave the stack in a state you got it when you entered that function. So you can execute other stuff on that stack without interfering with whatever has been suspended. It's a bit difficult to grasp, but I think you get it. Yes?
And then the future that then will resume, your future that then you return will resume at your await. Is that correct?
No, it will be, the question is, that return future will resume that await. That await will be resumed by that future. You're waiting on something. And that thing represents the overall result. So when both awaits have fired, that one gets ready. Yes?
What is the value of threshold in usually?
That's my zero threshold I'm using to cut off the...
When you show the diagrams,
Yeah.
does it depend from the threshold?
The question is, what is threshold? Yeah, definitely. The diagrams I showed, the x-axis was that threshold. So it helps me to find the proper sweet spot.
So you take from this diagram, you just take on the minimum like this number.
Yeah, it's just trial and error. So in that case, you look at the diagram. Okay. Passes parallelization results, outperforms any library-based solution so far. Scales better, runs faster, uses less memory. Well, I have to admit, we don't have a compiler to do that. What I just did, I sat down and converted the code by hand. same way as a compiler would do it when it saw that await statement. So it's handwritten code, and it's 2 pages, and we can have a look at the talk at that. So, but it's fairly straightforward transformations. So let me show the numbers. That's what we got with our .then solution, the scaling, speed up, number of cores, Fibonacci 40 with threshold of 28, so the optimum case. We get very fairly nice scaling. Well, the end here, you have to know that HPX is very aggressive in taking over the cores. And that was a 24-core system, and the operating system wasn't happy with me to take over all of them. So it said after 22 cores, now I want to keep 2 cores for myself. So the operating system just killed my scaling. But up to 22 cores, it scales nicely. But now, are you sitting tight? Good. That's what you get from the weight. A scalability massively improved. And still scaling, no end in sight, right? It's almost linear. Last thing, and then I shut up. Wait, please don't kill me. Yesterday, Thomas Haller, who works very closely with us, the co-author of Boost Phoenix, some of you might know him, just committed code to our repository, which he came up with a library-based solution. And I was really impressed because I didn't know that was possible. And what he did, he just created an object or a function which called data flow, which returns a future, which takes a function as its first argument and a couple of futures after that, and it makes sure that this function gets called whenever those futures get ready. Okay? So it's like data flow, right? A black box with inputs. When the inputs are there, the output is calculated. And the output is calculated by that function. And what he did, he implemented that using the same transformation techniques Await is actually using underneath. So that's a very badly looking code, really ugly, Boost preprocessor magic all over the place. It's horrendous. But guess what? It runs as fast as a Await thing. So we can do it with library-based solutions, but we have to have special constructs. And by the way, that's a construct we have been looking for a year now, to find the proper representation in the API, which makes it usable, very functional, but which still makes it manageable, and which gives you perfect, almost perfect scaling, perfect parallelization. But we could write that only after we discovered the futurization technique, because that relies on everything being that futurized algorithm. Okay? Okay, so what's the deal? That's my last slide. Then Vinay is on. Too much parallelism is as bad as too little. If you have too much parallelism, just overheads take over, and you're doomed. There's always a sweet spot which you can determine, or which you can find by controlling the granularity of your algorithms. And each algorithm has its own way to control grain size, the amount of work to be done in one unit of execution. And it's determined by the 4 horsemen. One end is overheads, the other end is contention, waiting, starvation. Granularity control is crucial. The grain size depends very little on the number of used resources, which is an interesting observation. I haven't shown any numbers showing that, but take that away. And the optimal grain size is determined again by the 4 horsemen. Even problems with quite strong dependencies can benefit from parallelization, like Fibonacci. Doing more is not always bad. And avoid explicit suspension as much as possible. Prefer continuation-style programming. So that's my message to you. Yes? You have a question? No? Do you want me to do that, or do you want to talk about that? One last thing. I talked about Amdahl's law, and if beta is 0, we get Amdahl's law. Okay. What this shows you is a extended law, as extended model of performance, which allows to introduce contention and latencies and all those 4 horsemen into a formula. And what you get is essentially a set of curves depending on alpha and beta, as I said, if beta is 0, you get Amdahl's law, and if beta is the latency, and that whole thing represents the contention and so on. But what I wanted to show you, and that's important, that's why I bring it up, you can use that law by having a couple of measurement points of your performance over the number of cores and the speed up to predict the optimum number of resources to throw at a particular problem. So just by running your algorithm with different number of cores, you can figure out by very little probing what's the best number of cores to use for that particular algorithm on that particular machine for that particular phase of moon and for that particular weather out there. Okay? That's why it's important, and it works. And Vinay will have a couple of examples how that kind of works together. Okay? Using HPX. Vinay, you're on. And I'm sorry for overdoing. Oh, the mic. I'm sorry. Even more delay.
Thank you, Hartmut. I'm Vinay Amatya. I'm a grad student at LSU, and I work with Dr. Kaiser. So what we have in the previous part of the presentation, what we learned is the different ways of parallelizing asynchronously. What I will talk in this and the remaining part of the presentation is how we use those features, asynchronous way of doing computation using HPX, not only in a SMP environment, but also in a distributed computing environment. I will talk about the features that you would require for asynchronous computation in HPX or actions. They are basically not very similar to, take example of your global function, very similar to conventional sense of what a function is. But in HPX, you additionally could invoke them at a remote locality. Or locality by locality, it means node. Here is a simple example of how a global action would look like. So I define a global function, and then I define that global function as a global action object in HPX. Using that, now using this example shows how we use the HPX action in a simple example of evaluating factorial. Here again, I declare the function. I define it as a HPX object, action object, and I simply invoke that HPX action object. I will come to here. This will HPX find here will tell that I invoke that function in that locality or the same node. We'll talk more about this a little bit later. And that's a way of doing asynchronous computing with HPX.
I have a question.
Sure.
How do you ship over the code from one node to the other?
So the question was, how do you ship the code from one node to the other? During the macro we define over here allows the runtime system to figure out that what systems can support that object, and when we I will come to more explanation a little bit later, but essentially we use global identification name or global name tag using the global address space to invoke that action remotely.
The code needs to reside in both locations beforehand?
Yes. Yes.
Okay.
So what are the HPX provides you a couple of methods of invoking actions. One of the method is asynchronous invocation with synchronization. which basically means you are invoking an action and the controlling thread doesn't care about the starting of that action or finishing of that action. Sorry, this is about without synchronization. So again, that is still valid, that the invocation of the controlling thread doesn't care about the start of the function or the end of the function, and also it doesn't care about the result value. Asynchronous actions with synchronization. Now it is the same, where you invoke the action asynchronously, meaning the controlling thread doesn't wait for the action to be invoked or finished. But we would, in some instances, we would like to get a value, for example, right? So I would call a future after get to for the function to return the value. So I synchronize at that point. Another method of action invocation, synchronous actions, which these actions get scheduled immediately, meaning it's very similar to your normal functions invocation in normal C++. The only difference is it is defined as a SPX action object, which could be used as a synchronous object, synchronous function call at that place, or it could also be used later on. Another method of invoking actions is continuation style action invocation, with the actions being asynchronous, and we would want to synchronize the resulting value. This method is very much similar to action invocation with synchronization. Let's go through a quick example how it would look like. So let's say I have two functions. I define two functions. I define it with the HPX also. Now I would call HPX async continue to with the first action object, the first action object, right, which is defined over here. Action object as the first argument, then the locality or the node where I would want to run that function, the input value for that function, and additional function object that will allow that the action to continue to the next action. This is very similar to what you do future.then in C++ with latest C++ 11. Now when I do the f.get, it will evaluate the first function with the argument, and the result value is sent to the next function. And when it is synchronized, it will produce the resulting value, synchronized value. So if I send, say, 5, the first function is just I'm adding 1, and the second function I'm multiplying the result or input value by 2. So this will be the first action, and the second action, or the continuation, would will use that input value. Additionally, in HPX, you can also do this continuation style programming action invocation at the remote locality. For that, whatever we have here in the second, where I define the function, the continuation function objects, here I also add another input argument, which is the locality where I would want to do that. In this case, here I am pointing to the same locality, but I could also do that with a ID of a different locality or different node. So that would allow me to do a continuation, do an action in this location, and then the continued action with the input value will go into the next locality, and the result value will come back to where it was initially started. Yes.
Is there a facility to load balance where this code runs and execution? You said it goes to remote.
The question is there a method of load balancing between nodes?
Right. I mean, I suppose specify where.
No, this is right.
But how do you specify where it needs to run? It should go to the same place, I think.
Right. This is a feature that we have to support migration, which is not there yet, but which would be used for load balancing of tasks when in a distributed computing. Right now, only load balancing of local actions can be done, but this is only just a feature at the moment. So load balancing across node is still under development. Again, the same thing, but here we are chaining the continuation style asynchronous action invocation with the first action, and then I will continue to the second action, and then I will continue to the third action. Last method of invoking actions in HPX is very similar to the continuation style action invocation. Again, without worrying about the return value. Like for example, I want to send a string, append a greeting to that, and then print out where I don't care about the returning value. Another feature that we have in HPX for asynchronous computing within one locality or for distributed computing is components. Components are your class in general sense, in C++ sense, but they can be instantiated remotely. In HPX, components are first-class objects, meaning they have a name, which are globally unique. The context of the instantiated components or objects would be preserved until the client, until the context within the client that holds the reference to the name, the global name for that object, does not go out of scope. I will come to the global name a little bit later. We also have a component apart. So whatever action types that we defined earlier are plain action types, which are basically for global functions. Component actions are the ones which, like for member functions of class. So how does a component look like in HPX? Which is, if you see, it looks very similar to how you define a class. You just inherit from the components base, and additionally you have to define the member functions as HPX component action type. So how do I use the components? Invoking HPX new with the component type accumulator will give me a global pointer, global name pointer called ID, and this will declare the member action of the member function defined within the component, and I would invoke it asynchronously. I could invoke asynchronously the member action type, and with the component ID. This is not the locality ID, but the component ID. So that tells me that action type belongs to that component which is instantiated over here, and I give the value. So this is another example of invoking the component action synchronously, and this is again fire and forget invocation of the component action. Here we talk about using the concepts that we discussed to evaluate a value that we all are familiar with, using a real-world methodology that people use in science, in research. It's basically we use an embarrassingly parallel method, which allows, by definition, these applications are easy to parallelize, meaning you can evenly distribute a workload among evenly distributed in equal size or chunks across the available cores. This is okay. Another feature of embarrassingly parallel applications is there is very little data dependencies, so we should get a good scaling. This is again pictorial representation of embarrassingly parallel, where each of the individual member tasks are independent and I don't do any communication. The method to evaluate pi is Monte Carlo. It is a way of simulating physical phenomena using randomness. The method is you generate a large sample of input data using with random character. I mean, using randomness, and evaluate that input. Evaluate a value using the input, using those inputs, and finally you get the average of the results. The results are an approximation of a true but unknown value. The method to use to evaluate Monte Carlo, I mean pi using Monte Carlo, you just have a circle fitted within a square, and I would use random numbers to figure out the area of a quadrant, for example. Here, say if this is the side is 2, then the radius is 1, then that will go 1, then pi by 4. So that's quite obvious. I will to evaluate that the first quadrant. I would use a more effective way of doing that. I could also evaluate using 2 random numbers between 0 and 1, and figure out if they fall within the circle using that equation, and dividing the total observed value within the circle or the quadrant by the total observations. I get the value of, and then multiply. I get the value of pi. But this is more effective, where I could, from 0 to n minus 1 observations, I could evenly distribute those to multiple processors. It's a quick synopsis of how I would use HPX to evaluate pi Monte Carlo. This is again global function that would evaluate a part of that value. That's so. This one here, I will try to figure out the HPX final localities will give me all the nodes that are registered with the HPX system. So it will tell me if I have like 16 nodes, then this will return a vector of 16 objects. That's the function for evaluate action. And after knowing the localities we have, I just invoke asynchronous actions for each of the localities. And then I call a wait for all future, which ensures all the actions have been completed. And I assimilate all the values. That will give me the result will give me the area of that quadrant, and I multiplied it by 4. That will give me the value of pi. This is just a time graph for the experiment with the pi Monte Carlo, where we observe that as the number of iterations increase, the value of pi becomes more stable. So this one is the lower one is with 5k iterations per thread or per core. This is for with 10 iterations, and this is for with 20 iterations. This is a scaling graph for the same observation, where I compare it with the universal scalability law that Dr. Kaiser mentioned earlier, and which is and we observe that the latency is quite minimal, but the contention is a little bit more. This was a straightforward implementation using the future.get. Using the various parallelizing techniques that Dr. Kaiser mentioned earlier would allow us to get a better scaling behavior, because the graph we are seeing, it does not show any good scaling behavior. Another example we looked into is FFT transform. Everyone perhaps knows what an FFT is used. I mean, in many applications, useful applications. It's a well understood problem that requires a lot of communication between the data points. Namely, we have ordered it as a butterfly communication. But using async could give us some scaling behavior. The implementation we tried was with the straightforward one, the Cooley-Tukey algorithm with radix to decimation in time, which basically means I am dividing the input into odd and even part, meaning two odd and even parts, and then I do the FFT transform and then go up. This is again the scaling result for the FFT transform, which shows I have a latency more than what we saw in the embarrassingly parallel problem. This is more of a the problem size is fixed, so I was trying to simulate a strong scaling example. So a lot of latency, of course, a lot of overhead. This is another result for the same experiment, and with that, I would like Dr. Kaiser to conclude. Thank you.
Well, essentially all what's left to me is to talk about the conclusions. Thank you. So all what's left is to talk about a couple of conclusions and the takeaway messages for you for this talk. So be aware of the four horsemen. Even if you are not religious, be aware of them. they kill your scalability and your effort in parallelizing something if you don't take care, or if you're not aware of the effects they might have on your efforts. Embrace parallelism. It's there to stay. Well, the newest cell phones have 8 cores nowadays, right? It's more than my laptop had 2 years ago. So we have to deal with that. Asynchrony is your friend if used correctly. And asynchrony is a way to deal with parallelism and with allowing to hide the concurrency. And the standard gives you the means for that already today, namely standard future. And if you are not satisfied with the performance of the standard future implementation in your standard library you're using, why don't you try HPX to do that for you? And we will be willing and able and more than welcome to do that. Think in terms of data dependencies and try to make them explicit in your algorithms, because data dependencies is essentially what's limiting your parallelization efforts, because the data dependencies define the synchronization points inside your algorithm. And if you make them explicit, you can use techniques to do parallelization, as I outlined in the beginning. Avoid thinking in terms of threads. Forget about threads. They're not there. All you have is cores and tasks and functions. And make sure those functions have no global side effects, because that will just destroy your effort, because you can't reason about that anymore. So encapsulate the right-hand side of your expressions in the way that you can async it and can load it off to a different node. Continuation style and data flow based programming is key for successful parallelization. That's a claim I make. And I think data futures are a nice step in that direction, but what we really need is a really data flow construct, as I outlined, which helps to kind of not only build very nice abstractions for parallelization, but also to get the performance out of the implementation we need. And last but not least, performance modeling can help you to adjust the parameters of your parallelization effort. And USL, Universal Scalability Law, is, just Google it, you will find it, is well known since 1995, I believe, but almost nobody talks about it, strangely enough. But it's really the tool to be able to do runtime adaptive decisions about how much resources to use for a particular piece of code. Well, the last thing, where to get it, there's a GitHub site, you can get it there. It's Boost licensed. We have a website, you can go there, there's some additional information there, documentation and so on, and 2 mailing lists. Feel free to subscribe and get in contact with us. I didn't put it here, there's an IRC channel, which is essentially the easiest way to reach us, because there's all day long somebody's there. Thomas is in Germany, so he is sleeping when we're working and vice versa. So you always find somebody who can help you with your problems. Well, that's it. Any more questions? Yes, please.
Can a node be another process on the same computer?
The question is, can a node be, or what we call a locality, another process on the same physical node? The answer is yes.
And in that case, do you communicate between the nodes with shared memory?
The question is, do we communicate between the nodes with shared memory? The answer is yes. HPX has several means of communicating with other localities. The default one is TCP/IP, which has its limitations because of latencies and so on. We have a InfiniBand parcel, what we call the messages are called parcels in our world. So InfiniBand-based transport layer, which gives us very good latencies. And we have a shared memory implementation to allow on-node inter-locality communication. So that's all there.
Do you have the infrastructure in there to manage process lifetimes? Like if you need to fire off a process to calculate a future, do you have the mechanisms in there to start and stop that process on demand?
The question is, can we manage the lifetime of processes in terms of Linux processes or operating system processes, if I understand that correctly? What we currently do is launch the same executable on all nodes at startup time. That's the way things are handled by HPC system nowadays. And that's because they have these scheduling systems, and the MPI jobs are always launched that way. And short of inventing new batch schedulers on the HPC systems, just for us, we just piggyback on that same mechanism. But what HPX provides you with is the ability to add more localities at runtime. So you can expand the footprint of your application, and you can shrink it. But in order for a single future, it probably is way too much overhead to do that. So you probably just invoke that future on a existing locality. But if you really want to expand, you can do that. Another thing what you want to mention is that these global IDs, the component IDs, are globally garbage collected, which is needed because you create a component and then you send that ID to 100 other nodes in your system. And now, good luck keeping track of when the last reference goes out of scope. So we have a reference count-based garbage collection scheme globally in the system, so that the last reference to a component, when it goes out of scope, the object gets discarded, which is very convenient. Other questions? Yes?
Well, what compilers and platforms do you support?
What compilers and platforms do we support? We support, well, Linux, GCC, and Clang. Do we support Clang on Linux yet?
No comment.
No comment.
We should support Clang on Linux. We don't have a builder set up for
Okay,
it.
but we support Clang on Mac. So it shouldn't be a problem to make it work on Linux. We just haven't done it. It runs on Android platform, which is nice. So it runs on my cell phone. It runs on Windows. That's mainly because I'm a Windows guy.
Xeon Phi.
It runs on the Xeon Phi, which is really nice. So you have that accelerator support. And Xeon Phi, for anybody who doesn't know it, it's a Intel accelerator card you can plug into your computer, which gives you essentially 240 cores. Each of them running Linux.
It works with the Intel compiler as well.
And works, yeah, Intel compiler is required for Xeon Phi, so Intel compiler. So we try to be very portable. And by the way, the reason why we are portable is because we use roughly 35 Boost libraries. So HPX is built on top of Boost, coroutines. Oh, well, I can't list them all, so just have a look at the code, which makes it portable. On the other hand, it makes it a management nightmare, because try to convince an sysadmin to install a Boost version somewhere. And even if you convince him to install a Boost version, he will install a version which is probably 10 years old. They're very conservative. So there are different things which we have to.
So on those platforms, if you can build Boost, you've got all the dependencies.
Right,
that you need to
right.
build.
Well, coroutines, the question is, once Boost builds, we can build our stuff. The question is probably a slightly weak yes.
How is the C++11? Is that required?
Is C++11 required? No. We have explicitly not required C++11, but we use Boost Move to emulate Boost semantics, move semantics. So whenever you have C++11 enabled, you get full move semantic support. And by the way, if you invoke an action which accepts its arguments as move, as R-value references, and you invoke it remotely, there are really only two copies made of the argument. One to get it serialized and one to get it out of serialization. Everything else is move enabled. So we try to optimize this as much as possible if C++11 is available. Other questions? Yes?
Do we have support for canceling tasks for things like speculative execution?
Do we have support for canceling tasks and speculative execution? The answer is yes. We can interrupt threads with the same semantics as Boost thread is doing that with the cancellation points. The same is experimentally implemented for futures, so you can cancel a future, although I don't like that because a future actually doesn't represent the operation, but it represents the result, and put the cancellation on the future is kind of, so that's not set in stone yet, but yeah, you can do this kind of things. Other questions? Yes, please.
What's your error model? What happens if a node fails while you're waiting on another node for the result?
What happens if a node fails and you're waiting for the result? The answer is very simple. You have a problem. I know it's not. Well, let me put it that way. If I invoke an operation on a different node and it throws an exception,
No, not falling reception. Really shuts down.
Okay, if somebody trips over the wire or the node goes down, then you just have a problem, because we don't have, well, until your time frame runs out, right? You have some time allocated for your application on the machine, and the scheduler will just kill you. So we don't have resiliency built into that yet, but that's on the list of things to do. One more thing. What happens if the remote operation throws an exception? That's an important thing for a normal operation, right? And what happens there is that the exception is transfers back and is rethrown at the .get when you wait for that operation. So that works very nicely. And you actually don't see whether it's remote or local. And all you do, you pass your ID, which references the thing you want to work on, and the system figures out whether it's local or whether it's remote, and does that for you. So you don't care, essentially, how it's done. Yes, please.
Along the same lines, when you send a request to a remote node and the node goes down just because of hardware failure, and so is there a built-in fixed timeout that you use for your futures to return, or is there?
The question is there a timeout to recover from serious failures in the system? The answer is currently no. We currently really rely on 100% reliability of the system. And I know that's a weakness, because when you think about exascale machines, the expected median time to error is minutes on those machines. So you have to embrace those system failures in your system, otherwise it doesn't work. But our reasoning was, let's get the functionality in place first and coin out the APIs, get the thing working, and then, well, somebody on the internet might be interested in resiliency and just adds it. So the whole thing is very modular, so you can do whatever you need. We can only do so much. Yes, please.
So how do you compare your approach with actors and actor libraries?
How does this compare with actor libraries? Well, actor libraries normally have a queue associated with an object where you queue up the incoming messages to be processed by a particular piece by an object on the other end, which serializes the operations for that object. We don't do that. It's really it's kind of active messages where you encapsulate the work, send it over, execute it, and get something back, with the addition of continuation style possibilities, so you can pass along the continuation to execute whenever that thing is done. But we don't queue it up, so you don't have this synchronization in place. It's very similar, it's slightly different. You know, when you look at that, you might say, hey, that's all known. Futures are there, actors are there, data flow is there, and some of you have not been even born when data flows have been invented. It's all ideas which are very old. But the trick here is that nobody has combined all those ideas into one coherent thing yet. And that's the actual new thing, what we do. So essentially, we claim that HPX is an implementation of a new execution model, which goes way beyond what we have today. Okay? Many things you will just recognize because it's already there. Yes, please. And then 2 more questions after that, please.
So when comparing with the classical MPI application where you have, say, fluid dynamics computation over a mesh that you've partitions, as well as you can, what would be the advantage of using HPX?
What would be the advantage of using HPX for conventional things which are already implemented with MPI? Well, not everything can take advantage of HPX. If you have a matrix multiplication, a linear algebra thing, MPI is just the way to go. Because every node takes the same time to do the same thing, everything works, lines nicely up, and so on. But once you have a problem with adaptive mesh refinement or with highly dynamic behavior where you want to follow the physics in your computational space, where you can't predict at compile time which node will actually take the most load of it, then you are just doomed with MPI. because MPI relies on that lockstepping model between all nodes doing the same thing all the time. So you wait for the slowest guy when you have some refined regions there. There, HPX can give you a huge benefit because it's highly dynamic. You have very constrained base synchronization. You wait only for the stuff you really need to proceed to the next step because it's fine-grained, right? And you get rid of these global barriers. Yes, Dave. One more question. Yes?
You mentioned using the compiler to build this tree of features.
Talk to Joel.
Okay, but my question is, how does that scale? As you get higher and higher numbers of features, does the compiler go linear, or?
He has an answer, apparently. How?
We implemented a subset of FlatPak, of Plasma, using HPX in NT2. And as it is already rather negligible, as with the speed up we get and the absolute time that we get is basically within 5% of what Plasma is giving us.
So it's in the range of the best hand-optimized code, essentially, right? Do I understand that correctly? The results you are getting are in the...
It's against Plasma.
Yeah, so it's good code you get from it.
But it wasn't that so much as the size of the problem increases, does the compile time increase linearly?
Does the compile time increase when your problem size increases? Well, talk to Chandler or somebody. No, yes, the answer is definitely yes. If you do that automatically. If you do it by hand, as I did with Fibonacci, then everything is okay. Yeah, please.
How would you compare HPX advantages and disadvantages against Charm++, which is older, maybe doesn't use modern C++ as well?
The question is, how do you compare HPX with Charm++?
But, bakes in a lot of the features that are still under development in HPX.
Frankly, let me listen to your talk and then we can talk again, okay?
Okay, sounds good. Thank you.
Bryce?
I just wanted to really quickly mention, with regards to fluid dynamics, if you want to know more about what we're doing with fluid dynamics with HPX, come find me later.
Yeah, we have a couple of applications already in works which use those techniques. Okay.
Yeah, on the same note, the fluid dynamics application. So it's not necessary that you could use something other than MPI if you have more complex physics going on there. If you have dynamic phenomena, if your meshes are adapting, which was Dan couldn't talk yesterday. Or even if you're, right now your application might be static, but your runtime environment, the execution environment might be dynamic. Your operating system, daemons and everything might be interrupting. So you may not have static load balance, right? So even in that context, something like HPX or Charm++ would be very relevant.
You'll get the speed up in that sort of code because in MPI, you're never going to be computing multiple time steps at the same time. With something like HPX or Charm++, you can find ways to do that. You can find without violating your CFL conditions. And that's when you can get speed up. But I won't get into that now.
Okay, thank you so much for staying 10 minutes longer, and I apologize for cutting into your break.